What we're going to look at here is we're going to look at a special technique for integration called integration by parts. Now what this allows us to do is integrate slightly more complex functions that take the form of a chain rule, i.e. two functions multiplied together. Now it's something that we have to be able to do. It comes up very, very frequently in exams, and it's a technique that allows us to be able to integrate these much more complex functions in a much easier manner. And it comes about from assumptions that we have to make. Now let's imagine we take a pair of functions, f of x and h of x, and we use the product rule to differentiate them. This can lead to a special rule for integration. So if we have f of x, h of x, and we take the derivative, d by dx, of f of x times h of x, we know that we can use the product rule in order to calculate the derivative of that. So what that means we get f dashed of x, h of x, plus h dashed of x, f of x. Now what I've got here is the derivative. So if I then do the counter derivative, i.e. the antiderivative, and integrate that, what I'm then able to say is that f of x times h of x equals the integral of f dashed of x, h of x dx, plus the integral of h dashed of x, f of x dx. Now what I can do is rearrange this side such that I'm looking for the integral of the f dashed x, h of x part here. What I can do is rearrange it and rewrite it as the integral of f dashed of x, h of x dx equals f of x times h of x, take away the integral of h dashed of x, f of x. Now what this is what's called integration by parts, and it allows us to make the assumption that our original function we're going to integrate takes the form of f dashed x times h of x and integrate it with respect to x using this formula here. Now there's a much simpler way and a much easier way to look at it that I prefer in terms of slightly simpler letters. We assume then that it's the integral of u dashed v dx that equals uv minus the integral of uv dashed dx. I prefer this assumption because it eliminates all the unnecessary complexity involved when we start using functional notation, and it's a slightly quicker and easier way to do it. Bottom line though is it's the same format. We have to assume it's the product of two functions and take one of them to be the derivative and the other one to be the original function, so that we can then calculate both the derivative of the original and the integral of the one we've assumed to be the derivative, and then plug them into this formula. It's a lot of words to throw at you, and it sounds a lot more complex than it is, but it's actually fairly straightforward and easier to use as long as we remember some of the rules associated with it. Now an easy way for me to do it is to look at an example. So let's imagine I want to integrate x cos x. So I want to calculate the integral of x times cos x dx. Now this sort of integration here, what we want to do is do the integral of u dashed v dx equals uv minus the integral of uv dashed dx. Now a key rule to remember here is what we want to do is choose the function v such that when we take the derivative of the function v, we end up being able to write the uv dashed in a format such that it allows us to integrate that function easier. So if I was to take, for example, the cos x and make it v, the cos x, the derivatives as you've progressed through would be cyclic. So if we chose v equals cos x, we know v dashed would be minus sin x. We then know v double dashed would equal minus cos x. We then know the next derivative would be sin x. then the next derivative from that would be cos x, and it would just continually go round and round and round. We would never ever get rid of that function no matter how many times we took the derivative. However, if I was to set my original function v to be the x, if I took the derivative of that, I'd end up with a constant of just 1. So I've essentially eliminated all the variables and all the dependence from that function upon x, and it makes it easier to do. So first thing we have to do is select the v and the u. So I have to select the v and the u dashed, and then from that I have to calculate the u, and I have to calculate the v dashed. So in this case, as I've mentioned, I'm going to choose v equal to x, so that means I can calculate my derivative v dashed is 1, and I'm going to choose my derivative u dashed to be cos x, and when I integrate that, I get my original function is sin x. So what I can now do is I have all the parts here for my integration by parts formula. I can just plug it all together and see what I get. So what I can then say is fine, so my integral of x cos x dx equals, well, the first part would be u times v, so x times sin x. Now, I know you're thinking to yourself, well, he said it would be easier because we're eliminating it, but remember, this has been integrated. It's this format here, and we're not actually taking the integral of that. So x sin x for this part is actually fine. We then want to take away the integral of u times v dashed. Well, u is sin x, v dashed is 1, so that is then minus the integral of sin x dx. What I now have to do is calculate this integral here, and I'm then done. So that's then going to equal x sin x minus the integral of sin x. Well, the integral of sin x is minus cos x, so what that then does is turns the minus into a minus minus, which is a plus. So I've then got plus cos x plus a constant of integration c. So that's me integrated that function. If I were to take the derivative of that, work it through, and then simplify it as much as I could, what I'd end up doing is getting back to my original function, x cos x dx. So there you go. I've used integration by parts, this new technique, to integrate it. This here is the key step, choosing the correct functions to represent v, u dashed, u and v dashed in order to make the integration easier than we wanted it to be. Let's imagine I'm now going to choose another example to show you. So I want to find the integral of e to the x times 2x plus 1 dx. Now again, think along the same lines as what we said before. The function we want to choose for v is the one that will eliminate itself as quickly as possible when I start to take the derivatives. Now in this case, if I were to pick v equal to e to the x, the derivative of e to the x is e to the x. And it would just continue to be that no matter how many derivatives I took. So I would never eliminate it with that no matter what. So what I'm going to do is I'm going to choose my v equal to the other function, 2x plus 1. Because if I then take the derivative of it, v dashed, I end up getting 2. I'm then going to set u dashed, my second function, equal to this part here, which in this case is e to the x. If I then integrate it, I get u equals e to the x. So now I have all the parts there. What I can do is then use the same formula as I've done before. So the integral of u dashed v equals uv minus the integral of uv dashed. Plug all the parts together, and I then get my solution. So I can say fine, so my integral of e to the x times 2x plus 1 dx, that equals uv, so this top part here multiplied together, so 2x plus 1 times e to the x. Take away the integral of u v dashed, well v dashed is 2, u is e to the x. Take away the integral of 2 e to the x dx. Integrate this part here. What I then end up with is 2x plus 1 e to the x minus 2 e to the x plus c. So there you go. That's me calculating my integral for that one, and I've worked it through and managed to get what I want from there. Again, this new rule, using it, helps me to get to that point that I want to get to. Now we can up the complexity a bit by making a slightly more complex function that doesn't eliminate itself on the first go. Now again, if you get a trig function, don't look at choosing that instantly, especially if you've got another function that can reduce itself. Now when I say that, I'm looking for one that reduces itself as quickly as possible. But if you think, looking at that and saying, right, well, if I take v being equal to x squared, that's not going to eliminate itself on the first go. That's fine. All it means is we need to apply it a second time to get the integral of the next part. Let me show you what I mean. If I choose v equal to x squared, I get v dashed equals 2x. And if I choose u dashed equal to sine x, my derivative u is equal to minus cos x. So what I then have to do is integrate it. So I do the integral of x squared sine x dx. That equals uv, so negative x squared cos x. That's then going to be take away the integral of uv dashed. So what that means is I'm going to have 2x times the minus cos x, so minus minus becomes a plus. So do that, plus 2x times cos x dx. Now this one here doesn't integrate straight away, so what I'm going to do is I'm going to take this one and I'm going to make it another integral I'm going to do by parts. In this one, if I choose v equal to 2x, my v dashed is equal to 2. So I'm going to eliminate it on this second cycle. So I'm going to do it again to this part to eliminate the first bit of the function and make it easier to do. I'm going to choose u dashed equal to cos x. What that then means is that u is equal to sine x. And I can then just plug it together. So I know that that's going to equal vu, so it's going to equal 2x times sine x. Take away the integral of v dash u, take away 2 times the integral of sine x dx. So I've got 2x sine x, take away 2 times the integral of sine x, or the integral of sine x is minus cos x, so that becomes a plus, so I get plus 2 cos x, plus a constant of integration there, c. So now that I've calculated this integral out here, which is this solution, all I do is I take this solution and substitute it back into the original function I've got there. So I can then state that my integral of x squared sine x dx equals this first part here, so minus x squared cos x, then plus the integral here, which is this bit here. So then plus 2x sine x plus 2 cos x plus my constant of integration, c. Now sometimes it may ask for a set format, so for example it may ask for it to be in the format of a cos x plus b sine x. So you've got two coefficients of sine and cos, and if that were the case for this one, I'd group the cos x's together and I'd have 2 minus x squared cos x plus 2x sine x plus my c. So just making it look as nice and neat as possible. So using this integration by parts technique allows me to integrate functions that we can assume take that format, and it all comes from about rearranging the derivative of the product rule of a function. So when we're working it through, particularly functions that take this sort of format here, using this technique allows us to calculate the integral. We just have to follow those steps, the key one being choose the v and the u dashed at the start. Remember, choose the v that we get rid of as quickly as we possibly can in as few rotations as possible.